Okay, so yesterday we saw pigeonhole principle. So now can you state the principle? Yeah. Quickly, loudly.
There are M pigeons and there are N holes and M is greater than N or N plus 1, then in at least one hole there will be more than one.
That's okay, right? So the pigeonhole principle is clear. I'm not going to state it. So we saw some applications in graph theory about understanding forbidden subgraphs. And number theory about approximating reals. Right. About approximating reals by rationals. And about information theory about limits of data compression. Is that okay? So this you should recall. So today let's begin with some questions. So this is something I think you have seen whenever you see pigeonhole principle. This is a standard question. Okay. So can you draw a graph? Can you construct a graph G? Okay. Let's say with 5 vertices. You can think of this graph as a social network like Facebook, LinkedIn. It's going to tell you which two people are friends or not friends. Okay? Two people who know each other or don't know each other. So this you may have seen as an application of pigeonhole principle, right? So 5 vertices here. You draw an edge between two people if they know each other. If they don't know each other or they are not connected through the network, then you draw an edge between them. Okay? So you want to construct a graph with 5 vertices such that there exists 3 people who are mutual friends, or there are 3 people who are strangers. Is the question clear? So you have to draw a graph on 5 vertices. You have to fix the edge. The number of vertices is fixed, right? You have to fix the number of edges. But either there should be 3 people who are mutual friends. What will that mean in the graph? A triangle, right? Or 3 vertices, or 3 people who are mutual strangers who don't know each other. So what would that mean? Independent set of size 3. So can you construct? You have to fix the edges. I have not fixed the edges, right? Have you already seen this, or do you already know the answer? You can just keep a triangle, right? Is that okay? I think that's what I wanted to ask. Maybe I should change. Okay. So let me change the question a bit. So if you want to construct, you can construct. Okay, so I'm changing the question. You can just put a triangle. The rest of them don't know each other. So now I want to ask, in any graph with 5 vertices, can you always say that there are 3 people who are mutual friends or mutual enemies? So now you can pick any graph, right? Each of you can pick your own graph. There are 5 vertices, so there are 5 choose 2 possible edges. Simple graph, let's say, right? Can you always guarantee that there are 3 people who are mutual strangers or mutual friends? If yes, you should prove. If no, you should construct a graph, right, where this is not possible. So what would you want to do? Okay. Yeah, C5, either I put the outer or the inner. Okay. So in this, there are no three mutual friends or no three mutual strangers or enemies. Is that okay? So can we always say? We cannot always. Right? Here is a graph where this is not true. So what about a graph with 6 vertices? So it's the same question with 5 replaced by 6. So is the question clear? So now we want to say pick any graph on 6 vertices. There are always 3 people who know each other mutually, who are friends, or 3 people who don't know each other. In other words, what is this in graph theoretic language? In any graph on 6 vertices, there is either a 3 click or a 3 independent set, right? That's what we want to show. I mean, is that true? Six vertices, 3 click, or this is a question. Okay. So 3 has no special status as such. Okay. So you can ask, is there a 4 click and a 5 independent set? Just started with 3. So this, so let me define. Okay. So let S and T be 2 natural numbers. I mean, this is the question we want to ask. We will answer this. So I'm sure you know the answer. Have you seen this before? Okay. So if you have not seen this, we will see this today. Okay. So S and T are 2 numbers. I'm going to call R, S, comma T. Right. That smallest number, the smallest n, okay, it's also a natural number, such that in any graph on n vertices, there is either ks, or I should say, should I say ks is fine, right? It means a click of size k, size s, or an independent set of size t. So this is what we will call R, S, comma T. R is called the Ramsey number. This is a notation. Okay. So what we have shown is, so what have we shown here? So we've shown that R33 is greater than 5. Right? Is that okay? Because we have said that the smallest number where there is either a 3 click or a 3 independent set cannot be 5. Right? So what we have shown is a lower bound on R33. This just says it cannot be 5. It does not say what is the actual value of R33. It has to be greater than 5. It's not clear. It might be 10, 15 and so on. Maybe it is 6 if you answer this positively. If not, it might be 7, 8. It's not clear. Is this a question okay? So if the question is not okay, you should ask questions and figure out. Because if we move forward, we are going to prove things. If the notation is not clear, or if something so far is not clear, you should ask. Is it okay? You got it clarified on yourself, right? So if you don't ask questions, you will lose yourself for the rest of the talk. You can also choose to do that, but you should be prepared for it. Okay, so this is what forms the basis of what is called Ramsey theory. There is nothing particular about ST. You can ask what is the value of R44, R55. We want to, how large can RST be? Can you prove upper bounds, lower bounds and so on? So let's stick to R33. So it's easy to explain. Okay, so what is another way to see this? Can you think about it? So it's saying any graph on n vertices, right? So it can start from, so let's say non-empty, so it can have one edge, to it can be the complete graph, right? There are so many graphs, and you want to say that it's the smallest number such that no matter what graph you pick on n vertices, either there is a clique of size s or an independent set of size t. So can you frame it slightly differently? Suppose I take Kn, taking complete graph on 6 vertices. In fact, you can do it for any n. So there are more edges. So these are the 6 people, right, who we are interested in. Let's give them some names. Okay, so 2 of them are either friends or they are not friends. Right. You want to ask, in any such graph, can you always say there are 3 people who know each other or don't know each other? So I have not drawn some edges, okay, I am not completing the whole graph. So what you can do is, can you use colors to identify who are friends and who are not friends? If so, how many colors do you need? And what are you coloring? So there are some people, 6 people here, 6 people, each pair can either be friends or not be friends. What can you do? I will also give you, let's say, some colors. I mean, you have to use the colors. I have given you some colors. So let's say I give you 2 colors, red and blue. I have 2 colors. So what can you use these colors to denote? Sorry?
Either G or G complement is by party.
Okay, so maybe I should phrase the question correctly. So there are 6 people, and there are some vertices, there are some edges. So it's a complete graph. So you know that there are 6 to choose too many edges. Right? Between any 2 people, they are either friends or not friends. And I have given you 2 colors. So you have to color code it. What will you do? Just color the edges, right? So let's say if they are friends, I am going to put red. Right? If they are not friends, I am going to put blue. Nothing complicated. So now can you phrase what RST is in this language? What are we asking? Correct. If it is 3, 3, right? That's what you are asking. In this complete graph, right? Is there a red triangle or a blue triangle in what coloring? So there is a graph which is Kn, right? Now the graph is fixed. So here there was any graph. So now I am going to fix the graph is Kn. Now what this graph is doing is, once you color the edges, right, it's telling you whether 2 people are friends or not, right? So what you are trying to do is, you are going to 2 edge color the complete graph, right? And you are trying to look for either a red triangle or a blue triangle in 3, otherwise a red clique or a blue clique, a red clique of size s or a blue clique of size t, right? So this any graph would mean that no matter what edge coloring you choose, you should be able to do this, right? Every graph here can actually be drawn like this, right, by using a coloring. I mean, when there is an edge, you put a red color, otherwise maybe don't put a color. So I will write it and then it should be clear. So you can think of this same number as the smallest n in n such that in any 2 edge coloring. So I am using some terminology. If it is not clear, maybe we'll coloring of Kn. There is so these 2 quantities are equivalent is what I am trying to say. Okay. So it's the smallest number n such that you fix Kn and take any 2 edge coloring of Kn. So you can color your edges as per your wish, right? There should either be a Ks or a Kt where all of the edges have the same color. So that's what we mean by monochromatic, a single color all the edges in that KS or KT have the same color. Maybe you should take 2 seconds to figure out why these two things are equivalent here. So instead of using this language, we will use this language. I mean, you can choose to do either of them. I chose to do coloring. So in this language, what would you mean R3, 3? See, it's strictly greater than 5. That is something we have shown. Right? Now, maybe it is 6. I want to check whether it is 6. Okay? So, if it is 6, right, I want to say it's actually equal to 6. Right? That's what I would want to say. I have not yet shown. I have shown one thing. I have shown that it's greater than or equal to 6. Now, I need to show it's less than or equal to 6. So, then I can say that the Ramsey number of 3, 3 is actually equal to 6. Right? So, this would mean greater than or equal to 6. So, what I have to show is less than or equal to 6. Right? To show it is less than or equal to 6, what should I show? I have to show that the smallest n, right, such that in any two edge coloring of Kn, there is either a K5 or a K3 or a K3, either a red K3 or a blue K3 is 6, right. So, what I should show is you pick K6, consider any two edge coloring of K6, there is either a blue triangle or a red triangle. So, maybe you should take 2 minutes to read what is on the board and figure out if you are comfortable before moving further. Okay, so maybe I will write the statement and then you can prove. So, these two things are equivalent. It's not hard to see. Maybe you should go back and think. If you stare a bit more about at the board, you should get it. Okay. So, what do we want to say? Consider K6 and any two edge coloring of K6. Then there is either a red triangle or a blue triangle. So, is it clear that this statement is the same as saying R3, 3 is at most 6? See, that should be clear. If it's not, then you have to step back. So, if we are able to say that, so we have shown that it is greater than 5. If we can show that in 6 there is either a K3 that is blue or a K3 that is red, then we have shown that the smallest number where this happens is 6. Right? So, R3, 3 is at most 6. The smallest is 6 and it's greater than 5, so it has to be equal to 6. So, if you have not understood anything that we did so far, this is an independent statement. It has nothing to do with whatever I said. Consider the complete graph, consider any two edge coloring. There is either a red triangle or a blue triangle. To get this statement, you need not actually understand all of this. So, even if you are lost so far, this statement you can still try to prove. Okay. So, this is the claim. So, do you want to try and prove? So, there are 6 vertices, you know that the graph is K6. You have to pick, there is some two edge coloring. Right? So, some edges in K6 are colored blue, some are colored red. You don't know which one is blue, which one is red. So, how do you show that there is a monochromatic triangle? Right, but how do you get that triangle is not clear? Okay, so there are 6 vertices, you are going to pick one vertex. Okay, so I am doing what she says, I don't know what she will say, so you should wait.
Look at all outgoing edges.
Okay, so let's pick a vertex u in K6. Okay. I mean there are 6 vertices, I am picking some vertex arbitrarily. Okay, so the choice of u does not matter, so that's what we mean by pick u arbitrarily. So, these are some English terms you must be comfortable with, because in the next lecture we will see pick a vertex uniformly at random. So, there is some meaning to it, right. Arbitrary means she picks u, you pick v, does not matter. Okay? The choice of u does not matter. Okay, and then you have to examine all the outgoing edges, right. That is what you said. Okay. So, there are how many edges? 5 edges. Okay. So, there are 6 vertices here, it is K6, so you know that there are 5 vertices. So maybe I'll put some more. So let's give all of them a name, I don't know. V1, V2. So have you seen this before? So someone who has not seen, can you try? Maybe you should wait. So far it is clear, right? She has done something. You have picked one, you don't know what to do, so you have to pick a vertex. And then there are 5 outgoing edges. The graph already K6 is 2 colored. So there is some coloring already, right? Or some of them are red, some of them are blue. So what should you do? There are 5 edges and there are 2 colors. So there are 5 edges, there are 2 colors, and you are sitting in a lecture using pigeonhole principle. What will you do? Just apply pigeonhole principle, right? So what will you get? So there are at least 3 edges that have the same color, right? So let's write that. Have same color. So I don't know, I'm going to give it some color. So I'll give blue. Yeah. I mean one of them I should use. Okay, so these 3. So again the choice of edges are arbitrary, okay, even these, the other could have been blue. Yes. So the other 2 are possibly red, or maybe all of them are blue, it's not clear. Right? It's a 2 edge coloring, you cannot guarantee anything else. Okay, so now what can you say? So it's a complete graph. So between V1, V3, V3, V5 and all, there are edges and they have some colors. We don't know what colors they are. So let's take V3, V5. I don't know. I mean all these choices are arbitrary, okay, in your notes you can take anything else also. What can you say? Now do you want to build the argument? So if V3, V5 is blue, you are done. Right? Okay, so let's record that. V3. Okay, so there's a blue triangle. So the other case is V3, V5 is red. So what will you do then? I think it's okay. Okay, hope I didn't mess up. Okay. So, okay, maybe I should give names. Okay. Yeah. I think it's okay.
Either red color and
What did you mean? So can you complete?
V1, V3, V5, all are connected by red color. Or there exists at least one pair which is connected by blue. Then only we can.
So maybe we should wait others to figure out. So there are 3 vertices and they have some edges. So I don't know. I'll draw in white. Okay, so it's a complete graph. So there are edges between these, right? So if all of them are red, all of these edges are red, I think this coloring is fine. Then you have a red triangle. Maybe that's not the case. So if that is not the case, what can you say? Amongst these 3, at least one of them is blue, right? So we should pick this one. Whichever one. That will give you a blue triangle. Right? So there is either a red triangle or a blue triangle by using pigeonhole principle. So this means that so I am not completing the argument, I think. 3 is at most 6. And also equal to 6. Right? Is it okay? So by pigeonhole principle, there were at least 3 that had the same color. Right? You look at those 3 vertices, those 3 edges and their outgoing vertices. You look at that triangle. They may all be of the same color, then you are done. If they are not all red, there is one blue, then you will get a blue triangle. Is that okay? So this has nothing to do with 3, 3. You can talk about R, S, comma, T. Right? And there are some known upper and lower bounds. So upper bounds are known. This also uses some variation of pigeonhole principle, and there are lower bounds only for some values of ST. Like 3, 3 we exactly know. There are some values where we don't know the actual answer. So this is what is usually studied in Ramsey theory about monochromatic cliques or independent sets. So we'll come back to it in the afternoon, but in a different way. Okay, so I will add one more here, which is Ramsey theory. So Ramsey theory itself has many applications. There are books on Ramsey theory. This is just an example. So is the argument okay? So there is one more problem which I wanted to talk about. Maybe we'll do it tomorrow. It's called the happy ending problem. So maybe we'll end with the happy ending problem. One more application of pigeonhole principle in computational geometry. Okay. So this gives some idea that pigeonhole principle, which you thought was a simple principle, is used in many places. So if that's okay, we should move to the next topic, which is so if there are questions you should ask, you should stop if you want to take a look. Okay. So maybe this is something you can go back and do a homework on why these two definitions are equivalent. You should go back and think. May require some thought, not much, but okay. So done. Okay, so you saw many examples of algorithms, right, in this course. So what are some algorithms? I mean, I don't know, so maybe you should say. Like matrix multiplication, I think Venkatesh talked about. And what are the other things? Vertex cover. Sorry? Minimum. Okay, so maybe you should raise your hand, it's a bit difficult. Minimum vertex cover. Okay. So you saw an algorithm to find the minimum vertex cover? Yes, you saw some algorithm. But that took a lot of time, I suppose. Right? Okay. Some exponential time algorithm. Okay. Then? Did you come across some other algorithms? Finding maximum, minimum, those kind of comparison based algorithms. I think Vaibhav spoke about testing whether a number is prime or not. Something like that he mentioned, right? About primality testing, given a number test. So all of these algorithms that you have seen so far are deterministic. Were you introduced to it? So can you describe what a deterministic algorithm is? Someone who had not seen this before but saw it in this course. What is a deterministic algorithm? So what is an algorithm? Maybe we should start there. So you are not aware of algorithms? If you are, you should answer. At least one of you should answer. So there is an input, you have to produce an output, and what do you do? And what does an algorithm do? Okay, so what kind of sequence? Should it be finite? Should be a finite sequence of steps that takes in an input and produces an output, right? That ideally solves the given problem correctly. But then you say this algorithm solves the problem. So there is an input, some box produces an output. So you can take whatever algorithm you saw. I don't know what ones you saw. So let's say you start with You have this algorithm written, maybe matrix multiplication, minimum, maximum, and you have an input instance, right? So one input on which you want to run this program. You run this program, you get some output, maybe maximum, right? And then I give the same input to this algorithm again, right? What will be the behavior of this algorithm? Same output, right? So if the input does not change, the same input is given to the algorithm several times, the output is going to be same. So does it mean anything? So it means that the output is determined by the input. That's what deterministic algorithm is. There is a finite sequence of steps and it will take exactly those sequence of steps on this input, nothing else. There is only one sequence of steps it will take. Once the input is fixed, right? Maybe on different inputs it will take different sequence. If you change the maximum where the maximum number is the first number, then the way the algorithm behaves on this and this might be different. Right? Here it may take only a few comparisons, for example in sorting, right? In sorting, depending on the sequence, right? On the set, it may read the set in a certain fashion, and for one input it may take 10 steps, and there might be another input on which it takes just one step, and that is possible. But if the input is fixed, then the behavior of the algorithm is determined. There is no change. So how many of your times you run this algorithm on this input, the output is going to be the same. Okay. So now, when I attended Venkatesh lecture, some of you were talking about randomized algorithms. Yeah, so someone who has seen randomized, I don't know how many of you have seen randomized algorithms. Okay, one or two of you. So maybe can you describe what a randomized algorithm is? So there is some randomness in this algorithm. I mean, in deterministic, there was some determined process. So in randomized algorithm, there should be some random process, right? There is some reason why it is named like that. So what is a randomized algorithm?
Where the output, for example, the random number generator.
Okay. So you mean the rand function in a programming language? So that is something tricky. So if you have a phone or some device with you, maybe you should try and Google this question. How random is the rand function? So you have heard of the rand function? So it's a standard function in C, C++ and all, where it will generate a random number. Ideally, in fact, you can give 1 to 100 and then it will generate a random number from 1 to 100. Right? So if you have done some programming, you may have used this function. Right? You call this function, then it will return a random number between 1 and 100. So can you Google? You all have devices, right? Yeah. You are like formally, legally allowed to use a device now. You have to Google how random is the rand function. I'm assuming you are Googling this. Okay. So.
It says it returns an evenly distributed randomly a number greater than or equal to 1 less than 1.
No, so how random is the rand function? What does it say? I don't know. No, please use Google. Okay, I don't know. I have not done it on ChatGPT, so it may say many things that I don't know of.
It's not truly random, it's pseudo random.
Okay, so it's not truly random is the answer. So you should put back your devices inside your bag. Okay. So the answer is not truly random. So there are two questions. What is truly random? Right? And why is the rand function not truly random? It is not clear. Right? It's not clear what is not truly random. What is truly random? That rand is not truly random. Right? And why is rand not truly random? Pseudo random is a different thing. So let's leave that. I think Arvind spoke about it. Okay. So that is something we'll come to hopefully tomorrow. Right? Why? When you Google this, you said rand is a random number generator, but appears that it is not truly random. So it's not clear what is truly random. So, okay. So what is a randomized algorithm? He said there is some randomness, meaning that the algorithm calls this function somewhere in the algorithm. There is a step that uses randomness. Right? So there is an input. There are some random bits. So this in a program would mean that you are calling the rand function maybe, right? And there is an output. So how do you generate random bits? Like if someone asked you to suddenly, like, can you generate a random number, random bit, what would you do?
The random function does it by looking at the time and then setting the seed using that.
Yeah, it does something that uses maybe like your mouse clicks or something like that based on some heuristic. But someone actually just walked to you and said, can you just generate a random number which is binary, just generate 0 or 1 uniformly at random. Huh?
Roll a die, 1, 2, 3.
But roll a die, there are 6 sides, so I don't.
Roll a die and 1, 2, 3, 0, 5, 6.
You can toss a coin. I think the likelihood of having a coin is more than likelihood of having a die, right, in your pocket. So you will toss a coin. So let's assume that this randomized algorithm has a coin. Okay. So and usually, so generally these are random bits, right? So you want either 0 or 1. So every time it wants a random bit, it's going to toss a coin. Okay. If it turns head, it's going to say that that bit is 0. Otherwise, it's going to say the bit is 1. So in a I think you saw Turing machines like Prakash introduced. So did you see deterministic Turing machines? Right? So the input in a Turing machine is this input tape. And this sequence of steps is done by a finite state control. This is input tape. And the output is written on an output tape. So what sits inside is a finite structure, right? Finite state control. So this is what he said, I am presuming. Right? So this is a deterministic Turing machine, meaning that if it reads this bit at this time, it knows exactly where to go, to this state. And there's only one step, one sequence it will follow. Right? So that's what, so deterministic Turing machine will loosely translate to deterministic algorithms in the world of algorithms. Eventually you have to run this algorithm, right? So you need a machine. And this is like the blueprint for that algorithm. So what about a randomized algorithm? So there is an additional tape which is called the random tape. Which has some random bits written on it. So you can think of this as, at the beginning of the algorithm, you toss how many ever coins you want, 100 coins maybe, write all the outcomes. Whenever the algorithm needs, it will go and read that tape. Right? So in the Turing machine. So this is called a probabilistic Turing machine. These are some things you should know. It's okay even if you don't know. So what I meant is that deterministic Turing machine is not a model to design randomized algorithms. You need random bits, right? Deterministic Turing machine does not have that support. Okay, so I think Venkatesh spoke about the P versus NP. I don't know if he did, but I'm assuming you saw P, NP and all, right? So P was this class of problems that have efficient algorithms which are deterministic. And NP, I think, are those class of problems where, so maybe you can say what is this class NP? Okay, so what are these? Who said that? You mean you cannot solve it in polynomial time, or we do not know a solution in polynomial time? So it is not solvable in polynomial time. Okay, so even he can solve one of those NP complete problems in polynomial time. Is those problems where we are currently unaware of a solution that is in polynomial time, but there is some more structure. It's not just that. It is verifiable in polynomial time. Right? So it's not that any problem for which you don't know a polynomial time algorithm is an NP. Right? It should be efficiently verifiable. Then it is an NP. Right? So it means that verification seems easier than actually solving. Or in other words, to verify you don't have to solve. Right? You just have to verify. Why would you go one step further and solve? So you saw about matrix multiplication, right? So let's look at that. So can you state the problem? Meaning what is the input, what is output?
Two matrices are input and their product is.
Product is the output, right? So there are two n cross n matrices, A, B, which are in. So you understand what F is, it's a field. If you don't understand, you can think about it as real numbers. Right? Reals, integer. I mean, integers are not a field, but you can think of reals. Okay? So we are going to do something slightly different. So I don't want you to multiply. I will give you the product also. You have to check whether it is a product. So A, B is the input and output is yes if so this is a decision problem, right? Yes, no answer. So what is minimum vertex cover? Is it a yes, no problem? If it is a decision problem, what problem is it? It can be formulated as a decision problem, but as is, what is it? Optimization problem. What about maximum? What kind of a problem is it? How is it optimization? What are you optimizing? What is the optimization function?
Comparison.
So you are looking for something. So it's a search problem. Optimization means that there is an optimizing function, right? Did you see SAT? So what did you see about SAT? So what problem is it? Decision problem. So suppose I give you a SAT. So I'll come back to this. What is the input for SAT? Variables and clauses. You mean a Boolean formula, right? Given as a bunch of variables. So maybe I'll put CNF. Not be necessary, but. And what is the output? Truth assignment. So let's say phi is on n variables. I mean, if one exists, else you have to say no. So what is one way to solve this? I mean, one way is brute force. Are there other ways? So while you're doing brute force, what are you doing actually? So this brute force algorithm for SAT. What is a brute force algorithm for SAT? Can you say? How long does it take? It takes 2 to the power n time. Right? What are you doing? All possible combinations you're going to check, and if phi of A is 1 at some point, you will return yes. Right? So maybe you are going to look at the whole truth table, let's say, right? And every time it's 1, you are going to record. So in the end, what can you do? So for every row, let's say you're also going to maintain whether it is 1 or 0 on this assignment. I mean, that's what the truth table does, right? The last column is whether it is 0 or 1. So if I add up the entries of the last column, what do I get? So the last column is telling you whether phi of A is 1 or 0. Right? I mean, you put a 1 if it is 1, otherwise you put a 0. So if you add all the entries in the last column, you will get some number, right? What is that number? Number of satisfying assignments, right? So this brute force algorithm actually does more. Using this algorithm, you can count the number of satisfying assignments and then check whether the count is greater than 1, which you are actually not asked to do. You are overdoing things. You are only asked to decide satisfiability, right? So there are counting problems where you have to count the number of solutions. You are given a graph, count the number of matchings, count the number of cycles. But there are many applications where you have to count the number of satisfying assignments. So these are generally like problems which are interesting, and most computational problems are classified like this. So SAT actually is searching for a satisfying assignment, but this brute force algorithm was doing more. It was counting the number of satisfying assignments. So how do you think it would be? Would decision be easier than counting? Should counting be easier than decision? It appears that decision is easier than counting, right? Yeah, so based on these you can define classes which are P, NP, NP completeness, all of these are defined. There are also counting complexity classes, right, where you want to count the number of solutions, and counting is believed to be harder than deciding. And verifying is believed to be easier than deciding, right? Verifying is easy is what we believe. Okay, so let's come back to matrix multiplication. This is a detour of everything that you saw. Okay. So what you are asked to do here is you will be given 3 matrices, you have to verify whether C is equal to A times B. Right? So can you give an algorithm for this? I mean some algorithm that you have seen already. Yeah, you said something. What did you say?
Simply multiplying.
Just multiply the matrices. You have an algorithm for multiplication. So multiply and then check whether whatever you get is the C. So what is the running time? So what is the algorithm? What is the running time? N cube. Okay. I mean, there are better algorithms for matrix multiplication, so you use the best known algorithm for matrix multiplication, right? So the running time is actually, but this is the exponent, right exponent for matrix multiplication. Today it is some value, I mean tomorrow it might be something, we don't know. What do we know? This is at least how much? Huh?
2.81 is plus Strassman's matrix.
Strassman's, but it's at least, it should be at least how much? Can omega be 1.8? Should be at least 2. I mean there are n square entries, you have to write down all the entries, right? So it's somewhere between 2 and maybe 2.37, which is the current best. Maybe it will get better, right? So whatever is the best known matrix multiplication algorithm, you can use that. Now the question is, should you multiply to verify? I did not ask you to multiply. I just asked you to verify. So can you do something better? So for multiplication, we don't know an order n square time algorithm. For verification, do we know an order n square time algorithm? That's the question. Because I've already given you an output matrix, right? What I think is the output matrix, you have to just figure out whether it is or not. So is there a better way to do it? So ideally, you should not multiply. Right? If you multiply, you are doing things, you are exaggerating things. So what else can you do? So let us assume that these matrices are 0, 1. And this algorithm will work otherwise also, I am just assuming this. And C is right. So C, A, B, all of them are 0, 1 matrices. Right? Multiplication is modulo 2. So you multiply the row with the column, you will get a number, you go modulo 2, it might either be 0 or 1, put that entry. This is for simplicity, okay? The algorithm will work irrespective of this. It's easy to describe. So maybe I'll give a hint and then you can try to figure out. So A, B are n cross n matrices. Right? Okay. And C is another n cross n matrix. So at the moment it's not clear whether AB is actually C, right? And you don't want to multiply, right? That's what you want to do. So let's say that I take a vector, let me call the vector X. So vector means a column vector, it's n cross 1, okay? So if AB is equal to C, what can you say about ABX? BCX. I mean, this is an observation. This has nothing to do with the algorithm, right? This is just something mathematical. If AB is actually C, then no matter what X you pick, right? So what is the advantage of doing this operation? So how do you compute this? Louder. Multiply with? So complete it, whatever you said. So either you can multiply A with B and then multiply that with X, or what else can you do? So what he said multiply 1 by 1, do B times X. What will this be? A vector. Right? Multiply A times B, which is another vector. I mean, you are multiplying a matrix with a vector. Right? So you have converted a matrix vector multiplication into two matrix vector multiplications. What is the running time? I mean, this, let's assume that you are using the worst multiplication algorithm. This would have taken order n cube time. Right? First you have to multiply AB, which will take order n cube time, and then some more multiplications to multiply it with X. So now what I have done is I have used this way of looking at it. So you might have heard of associativity, right? I can bracket things out, right, in steps. So because of this, what I have done is first I will compute B times X. How long will that take? N square time, right? So there will be n, this has size n cross n. You have to multiply with an n cross 1 vector. So this is some n square. So let me say order, some additions are all there. And then with this, which is a vector, you have to multiply this. How long will that take? Okay. So overall this is order n square time. So I have used matrix vector multiplication somehow. I have not used it in the place of matrix multiplication. Instead of computing this quantity, I have computed it like this in 2 steps. Okay. So how long will this take? That will also take n squared. Okay. So now if AB is actually equal to C, right, I can pick whatever X I want and do this, subtract this and check whether it is 0. And if AB is actually equal to C, I will get 0. So what if AB is not equal to C and I pick some X and do this, what will happen? So this has nothing to do with the algorithm. So I am not flashing the algorithm, right? So I am helping you design an algorithm based on some basic observation. Can you do that? So what he says is, it might be that AB is not equal to C, but ABX is equal to CX. Is it possible? If so, can you construct? Maybe 2 cross 2. I have some example for 2 cross 2. So is the question clear? Right. So if the answer to this was actually no, what would be an algorithm? Is the question clear? So suppose you are able to guarantee that if AB is not equal to C, no matter what X I picks, this will not be equal. What can you do? So the answer to this might be yes or no. Does there exist ABC such that AB is not C, but if you multiply it with some X, it's ABX is equal to CX? Suppose the answer to this is no, that is no matter what X you pick, if this product is not equal, then this will also not be equal. But suppose that is guaranteed, what can you do to design an algorithm? You can pick an X, whatever X you want. You do this kind of a multiplication, which is order n square times, subtract and see. If it says equal, you put AB equal to C. If it is not, you put AB is not equal to C. Okay. Suppose the answer to this question is no. Okay, so maybe I should write better. Suppose this is true. Then you can pick an X in 0 1 to the n, you can multiply and check. And this algorithm takes only order n square time. Right? But the problem is this is not true. So there are matrices A, B and C such that AB is not equal to CX, but somehow magically when you multiply with the vector on the right, everything becomes equal. So maybe I'll give one example. I think it's not hard to construct. I mean, you can also construct, but okay. So this is A, B, AB. Okay. So here AB is not equal to C. Right? But can you construct a 2 cross 1 vector? If you multiply on the right, it will be same. See. Right? So if you said, okay, consider an x in 0, 1 to the n and ask the algorithm to do this. First compute bx, then compute abx, compute cx, check if these two are equal. If AB is equal to C, it will give the right answer. But there may be cases where AB is not equal to C and still it will say yes. Right? If your choice of x was 1, 1. So that's a problem. So now what can you do? So 1, 1 was a particularly bad choice. There are some vectors for which you can actually witness that it is not equal. We were just bad with our choice. So now you can ask, can we count the number of vectors that are bad for us? Then we can try to avoid those vectors. So is it okay? So maybe you should read once from left to right. If you are comfortable, then we will move forward. So maybe I'll write the algorithm and then you can think. So let's consider this algorithm. It's not the right algorithm, but anyway. So pick any So I've written an algorithm, so maybe you should take time and read the algorithm. It's exactly what we did, right? You pick an x, multiply this and find abx, find cx, check if they are equal. If they are equal, output yes, otherwise output not equal. What is the running time? Order n square. So that's fine. It's a faster algorithm than multiplication. Is it always correct? No, right? So there is a problem. So it's not the right algorithm. So it's an incorrect algorithm for me. So this algorithm has one-sided error. So if AB is actually equal to C, it will always say yes. But it might be that AB is not equal to C and yet it is going to say yes. So that is something we have to correct. Right? One direction is doing job correctly based on this simple observation. But based on this example, it appears that there are some cases in which it is wrong. So what can you do? Suppose you were asked, but this algorithm, is it deterministic? I have not used any randomness so far, right? You can pick your own x And if you run the same input again and again on this algorithm, it's going to give the same output.
You can try for other X.
Right. Yeah. But the behavior of the algorithm will depend on the choice of X. So I cannot say it will always return the same answer. I mean, the first run, maybe you picked 1, 1 and you were unlucky. The second run, maybe you are picking the right X. Right? So you have to try for other X. So one idea is you try for all X. That's a bad thing, right? Running time is lost. So now you have some randomness. What can you do? So you have bit strings of length n. It's representing a vector, right? So there is this box that has 2 to the n vectors, and you can pick one uniformly at random from it. So have you heard of this terminology? Pick X. So what is the meaning of this uniformly at random? So how do you pick a vector at random? You have some coins, you have to pick a binary vector of length n. Toss a coin for every index, right? So you have to fill a random vector, it has n positions, right? Every position should be either 0 or 1. You have a coin. So toss a coin, whatever is the outcome you fill accordingly. So if you see a head, you put in, let's say 1. If you see a tail, you put in 0 and so on, you populate this vector. Is that okay? So if I do this, so what am I doing? I am doing a random experiment. And what is the experiment? Toss the coin n times. You fill this vector. So what is the probability? Okay, so if I toss n coins, say n coins, this is standard question in probability, right? Middle school. If I toss n coins, how many heads will you see? Huh? So there are many answers, so I am going to record each of them. At least n by 2, okay? At most n heads you are saying, okay, so this is a lower bound, it's one upper bound. So if I toss n coins, is it possible that all of them are tails?
Yes.
So how can you say at least n by 2 heads are there? It's incorrect, right? So at least n by 2 is incorrect. But there is something which he said that is correct, it's just that the English was incorrect. Okay. So this is okay. You are tossing only n coins, so you can see. But if someone asks you, you are tossing n coins, how many heads will you see? What can you say? You cannot see any heads. Maybe you can see 1 head, 2 head, 3 heads, not clear. So will you can never say, right, in a random experiment. The outcome is not defined, it's not deterministic, it's not determined, it can be anything. So what is the right English term I should use? Could, if it's not would see, then it should be could see, may see, but there is a mathematical term for it which you have seen. No high level terminology, just class 6 mathematics. You will see how many heads. How many heads do I expect to see? You cannot say I will see n by 2 heads. Someone will toss you a coin and say no, there are not n by 2 heads. But someone asks you how many heads do I expect to see, then how many can you see? N by 2. That's what you did in school and recalled from memory. So why do you expect to see n by 2 heads? Like I don't expect to see n by 2 heads. It appears that you are expecting, so there should be something. So the answer is correct. The question is, how did you answer that? Hmm?
Because they're equally likely, so
It's like binomial
Huh.
expectation.
So there are only two outcomes, and every outcome is equally likely, right? You can either get a 0 or you can get a 1. So let's give some names. So I'll come back to this, okay? So I don't think I have the time, so maybe we'll do some probability prerequisite and then. So there are two outcomes here, head, tail. What is this? Sample space. There are only two possible, set of all possible outcomes. Two. This is in one coin toss. Okay? So we are going to toss only once. Here you have to toss n times. So what is x? So x is going to be the outcome of coin toss. So there are two possible outcomes, head or tail. What is the probability for each of them? You said n by 2? 1 by 2. Okay. So now what is expectation? What is expectation of x? So let's say I should not give it head tail, let me give it 0 1. Yeah, so these things you are familiar, right? What is expectation? So this is for one coin toss, right? So now if there are n coin tosses, what can you say? So how did you say that? Came like inadvertently.
Nx, expectation of nx, n times of expectation of x.
Okay, so maybe I will put, it's not n times, so each is an independent coin toss, right? So you have to give independent names for it. So let's say x1, x2 to xn are the n coin tosses. Each is a random experiment. For x I have to toss the coin 1, I'll see head or tail with probability half. For x2 again I have to toss the coin. So this means that the coins are tossed independently of each other. So there is no connection between x and y. So it's not like, so there are also some random experiments which you have seen. Toss the first coin. If it turns heads, then roll a die. Otherwise toss a coin, right? I mean in nature you can find such experiments. So here all of them are independent, meaning the outcome of one does not affect the outcome of the other. There is also a way to write it in math, right? Okay, so now, so we want to understand the expectation of x1 plus x2. So what is this?
Reduce expectations, sum of 1 by 2.
Okay. So,
N times 1 by 2.
so how did you get this? I have not seen it.
They are independent, so we can separate it.
So what he's saying is expectation of a sum of random variables is the sum of the expectation.
If they are independent variables.
If they are independent, there was someone who said mutually independent. So what is this? This has a name in math. No, that's not the right term. You got it wrong with probability 1. Something else which you have learnt in school. Nothing in this course. Go back to school. Linearity of expectation, right? Why is it called linearity? So this is a linear function. It has degree 1. You are pushing the expectation inside, right? Which is true for linear functions. So f of a plus b is equal to f of a plus f of b means that f is linear, right? Okay, expectation. Does it require x1, x2 to be independent? Someone said mutually independent, so which I have not heard. What is mutually independent? Pairwise independent, you mean, is it? Whoever said mutually independent, you should think what is the meaning of the term mutually independent. So there are many ways, right? So there are n random variables, they can be pairwise independent. But if you take 3 of them, they may be dependent, right? Or they may all be independent, meaning you take any subset of them, all of them are independent. Then they are all independent, right? Nothing affects anything. So maybe you should go back and prove this, okay? That expectation of a sum of 2 random variables is the sum of the expectation, not even n. Just do it for two random variables which are 0, 1. Maybe to simplify things, you can say x is 0, 1, 0 with probability p and 1 with probability. So there are some outcomes, possible outcomes. Here there are two. If you sum the probabilities, they should add up to 1. So I'm assuming those things you are familiar with, right? So you should go back and prove this, that expectation of x plus y is equal to expectation of x. And you should come back and see if you need the fact that x and y are independent. In the proof, are you going to use it? So the proof will not require it. It does not, you don't have to assume anything about the random variables. Right? That is how powerful linearity of expectation is. You see expectation with a summation written inside, just push it inside. You don't have to think anything about what is written inside. It does not require any property about the random variables. They need not be independent, mutually independent. Whatever big jargon you need, there is no jargon that is required. For all x, y random variables, this is true. Of course, they have to be like finite inside whatever. Here there are only 2. Right? So finitely many random variables, it is true. So you should go back and prove this. It's not hard. You have to do this substitution. Whatever you said, right? The formula for expectation. For all x in the sample space. Okay, so you have got some introduction to expectation probability. So we have to go back and see how to modify this incorrect algorithm into a correct algorithm. The algorithm will use randomness. So I will give the algorithm an input and a coin. Whenever it wants, it can toss the coin. It will give me an answer, but the answer may not be correct, right? Because it is doing something random. So it is unlikely that the answer will always be correct, but the probability with which it will be incorrect will be low. So what is low I have to define, which I have not done. So you should go back and brush probability. That is the takeaway. If you did not get anything, it means that you have to learn probability theory again. Maybe now if you go back to class 8 and study, it will be much easier because now you have much more exposure, right? So when you see a terminology, you should ask why it is named like that. These are not meaningless names. Right? Linearity means there is something linear about it. Now you can ask, what can I do what can I say if I make this x1 square plus x2 square plus xn square? Where it's not linear but quadratic. So then what can I do? Can I say it's expectation of x square? Expectation of x the whole square, can I do that? So we will try to see some example of where linearity of expectation is used in an algorithm. So we will design an algorithm, we will analyze an algorithm, the analysis will use linearity of expectation. It will be a randomized algorithm. Okay, so that probably in the afternoon and then tomorrow. So if you find time, you can go back and read a probability theory. I mean, you cannot read it overnight. So I'm not suggesting tomorrow morning you should come with all the information. But there are some good books to read probability theory. It's a first course in probability theory. By Sheldon Ross. And there are many books, all discrete math books have a sufficient amount of probability theory. So we will follow a book called Randomized Algorithms. Yeah, I'll give the details in the next lecture. But if you generally want to learn probability theory, this has a lot of information. So much information is not required, but yeah, so the takeaway is that when you see a statement, it has some terms, there is some meaning to it, you have to think why it is called that. So why is expectation called that? Because it is what you would expect, not what you will see, right? So now you can ask, how far will the reality be from expectation, right? So those are questions where you ask, you have x is a random variable and you have expectation of x. Now x may not be expectation of x no, in most cases, it might be much far from expectation of x. How far? So what is the probability that x would be much larger than expectation of x? In these kinds of questions you can ask, right? How far will you be from expectation? You have studied these and you have applied Markov inequality, Chebyshev inequality, not just that you did not realize that is what it is doing. Okay, so in the afternoon we will see a correct algorithm and then analyze it.